It is 1 o'clock Pacific time. I want to welcome everybody to today's presentation on what's a perovskite solar cell and why should I care. My name is Patrick Nugent. I'm the Executive Director of Solar Washington. Today's presentation is by University of Washington professor and Clean Energy Institute Chief Scientist David Ginger, and he will be introduced by Solar Washington board member Sarah Vorpal. She's the Senior Energy Policy Specialist, specializing in distributed energy resources at the Washington State Department of Commerce. For a moment here, I will tell you a little bit about Solar Washington. Solar Washington is a nonprofit 501c3 organization focusing on providing educational resources and outreach pertaining to solar energy, its uses and benefits in the state of Washington. In addition to our website, we host presentations like this one today, other online and in-person events, Washington State Solar Summit each fall, a conference for solar energy industry professionals and advocates. I want to thank our annual sponsors and members who help make presentations like this possible, and also the individuals who are members of the organization. And for those of you on the call, we welcome your support for Solar Washington, which helps us make presentations and conferences and our other programs possible. To support us by being a member, you can visit us at solarwa.org on the web for more information on how to do so. I'd like to thank the folks at UW's Clean Energy Institute for making today's presentation possible. And just a couple of housekeeping announcements. I'm going to put everybody on mute. Please stay muted and do not unmute yourself during the presentation. Thank you very much. We will take questions at the conclusion of the presentation, time permitting. You may use the chat box to pose your questions, and we'll read from your questions, and we'll get to as many as possible, again, time permitting. And this webinar will be recorded. Other than that, I'm going to hand it off to Sarah to say a few words and introduce David.
Great, thanks, Patrick. Can you guys hear me?
Yes.
We can.
Fantastic. All right, hi everyone. So yeah, as Patrick said, my name is Sarah Vorpal. I'm a newly elected Solar Washington board member. I'm also a senior energy policy specialist focusing on distributed energy resources at Department of Commerce. And I also had the honor of earning my PhD in David's lab at the University of Washington. So it's really an honor and a thrill to get to introduce him in this work today. So just for a little background, Professor David Ginger is an endowed professor in the Department of Chemistry at the University of Washington. But as you can already see from this intro that Patrick mentioned, he also wears a number of other hats, including Chief Scientist of the University of Washington Clean Energy Institute, co-director of the Northwest Institute for Materials, Physics, Chemistry, and Technology, or UW Impact. He's an associate editor of Chemical Reviews, a journal, and a distinguished scholar of the Washington Research Foundation. David, you're making me feel inadequate. He received his PhD in the optoelectronics group at University of Cambridge and went on to do postdoctorate work at Northwestern before arriving at the University of Washington. His research centers on the physical chemistry of nanostructured materials with applications in optoelectronics, energy, and sensing. So kind of lots more than just the research you'll hear today, but also really exciting work in the energy field. And his group makes use of characterization techniques, including scanning probe microscopy and optical spectroscopy. His group has pioneered new methods using these techniques to reveal how the structure of emerging energy materials correlate with their performance in devices, especially for emerging materials such as hybrid perovskites. His lab has also produced dozens of scholars, researchers, and policy specialists, such as myself. And just on a personal note, I want to say that David's one of the most driven and thoughtful researchers that I know. And one of the best things he taught me was how to connect the work that we were doing in this really fundamental physics, around these fundamental physics questions at the nanoscale to the bigger story of how these new technologies need to have an impact in the world. So I look forward to your talk. And with that, I will pass it to you, David.
David, I'm going to make you a presenter now. There you go.
Great. And I will try to Oh, wait, I've got to get the technology working the way it was
Sorry
prior.
about
No, here we're getting back. And there we go. Can you all see my slides? Because
Yep.
they've disappeared from my screen.
Yeah, we can see.
Great.
I can see most of it. The hyperlinks are cut off a tad bit on the far right, but otherwise we can see majority of the slide.
Yeah. Okay. Well.
Yeah, it looks good to me, David. So yeah.
If you can't see parts, let me know and we can try and resize. It tells me it's actually showing you my whole screen with big black boxes on the end. So thank you, Patrick, for the invitation, and thank you, Sarah. It's a real treat to be introduced by one of your former students. And it's funny that you said I make you feel inadequate, because I wish I was having the impact in the world that you're having out there now. And so sometimes as a professor, we have to live vicariously through the accomplishments of our students in the real world. And it's something we do aspire to do, is have an impact. So thanks, Sarah. So what's a perovskite solar cell and why should I care? And I'll apologize in advance. Sarah said I'm going to tell you about some of my research. I might tell you about things we're researching on, but today I'm really going to keep it pretty general and really try to answer these questions. And also I'm going to try and give sort of a 50,000-foot view of where I see solar right now. And I'd love to hear the feedback, because I know many of the people on the Solar Washington calls are very active in the solar field themselves. And so I'm curious to see how my perspective, meshes with what you guys are seeing, literally on the ground. And so, come on, there we go. So before I get going, I did want to thank my current and past research group members. They're the ones who actually do our work in the lab. They're the ones who help compile slides, even the public slides that go into talks like this. And so you can see Sarah's name over here in recent alumni, although I think neither one of us will want to admit that it's been getting a few years now. As you can see, like the rest of you, we used to have group meeting photos where we would all meet in person every week, but this is how we've been meeting every week for the last couple months now. And as Patrick mentioned, I'm also chief scientist of the University of Washington Clean Energy Institute. We are a state-funded institute at the UW. We get about $3 million a year in state funding, and we've had about $15 million in additional donations and investment. And our mandate from the legislature is to accelerate the adoption of a scalable clean energy future through science and technological advances and workforce training for solar, storage, and smart grid technologies, right? All three of these are really interdependent. Today, of course, I'm going to focus on solar. That's the core of my own research mission. But I wanted to take a moment to embarrass Sarah, because as a university, we produce new knowledge, but one of the most important things I think we produce are trained people, and sometimes we take more credit than we should for training them. They come in with a lot of ambition, and if we do our jobs right, we enable and empower them to go and do things that they wanted to do. And Sarah, is an example of what I think is a really fantastic success story within the Clean Energy Institute, in being flexible and letting students pursue advanced technical degrees, but take those technical degrees in non-traditional paths, particularly into the policy arena, which is incredibly important these days, as we see, science and technology needing to inform public policy on everything from public health and the COVID pandemic to energy, which is familiar to all of us. And so after she left UW, she went to be a science policy fellow in Congress. And there you can see her and the office she worked in. And yeah, Sarah, it's amazing to be back here. So what am I going to talk about today is, what do I think the future of solar looks like? And I want to try and answer two questions that I'll pose here. The first, is there room for a disruptive new solar technology? And the second is, can we reestablish US manufacturing dominance of semiconductors for PV and optoelectronics more broadly? And I want to phrase it this way, because I often hear, and this is actually a good thing, I often hear people say, oh no, solar is done, right? It's a solved problem, we're there. the curve's taken off and we just need to sit back. And obviously, I disagree with that. I think we need to move faster, and I think we can move faster, and I'll share my perspective as to why. And the second is, I also hear people say, well, US manufacturing of advanced materials is done, right? Manufacturing is going to be done in Asia, predominantly in China, and so we've ceded our leadership in that industry, and it's not coming back. And I think there's an opportunity that we can bring manufacturing of advanced technology, particularly advanced materials for photovoltaics and optoelectronics, back to the US through technological advancement. And so I've answered my talk, but of course I have to give a disclaimer. I'm going to ask what the future looks like. I think this is a Yogi Berra quote, but right, he's been attributed many things that weren't said to him, but it's tough to make predictions, especially about the future. And so if we look in energy, just even in the last 15 years, things that people missed, right? Fracking was a huge mega trend that people missed, and the huge dramatic cost in the reduction of silicon PV that happened, even though it actually followed the historic learning curve. There were Department of Energy assessments that said we are not going to be able to follow the learning curve. The sunshot targets were set in a way that, in fact, they were met almost ahead of time. And so these are difficult predictions to make. And so why do I look forward? And I'm looking forward particularly with urgency to answer these questions. And I don't know who the original source for this comic is. I searched for it last night. I've seen it on Twitter. I've seen it on a number of news reports. But this was in response to the COVID epidemic, right? Here we're looking at flattening the curve for COVID, and everyone's now familiar with flattening the curve. And we're just, we're glad when this epidemic is going to be over, and then we see looming behind us, another curve that we are refusing to address and until maybe it's too late. And so I think climate falls into this in an area that we all, I think if you're on this call, you probably agree with me that there's a sense of urgency in addressing the global climate challenge. In fact, there was a recent study that said inaction, right, if we fail to limit climate change to less than 2 degrees C, could lead, it's a big error bar, but up to $750 trillion in lost economic activity over the next 80 years. And to put that in context, that's double the annual loss in economic activity that we're currently experiencing due to the COVID closures. So imagine double that economic impact sustained over 80 years. Of course, this is a time integral and it's complicated, but this cartoon for me really hits home in driving home the urgency of a solar adoption. The second, which I think also links to current events, is the urgency of dealing with global health and global equity. And so this is a topic for an entire separate talk, but I do want to bring up the fact that energy poverty deprives over 1 billion people worldwide of healthcare. Here's a photo from The Guardian from a few years back, showing how energy poverty affects how people read and study. These are young Guineans studying under the airport lights at night because that's where they can read. And I want to acknowledge that the policies that we as a society have used to promote adoption of renewables and fossil energy, to be quite honest, it's not really a problem just of renewables, have not always been the most just. And there's a lot of literature about that today on the health energy justice nexus. And I think it's something we have to consider going forward. So with global health, equity, and climate together, hopefully we can address these challenges for more positive outcomes. And so, do we need to do this? Isn't this a solved problem, right? For years, maybe the past 3 or 4 years, we've been reading articles about getting ready for peak oil demand. In fact, just recently, the CEO of BP, I believe, was asked if we've reached peak oil, and his answer was no longer no, it's in the future. He said maybe. I think maybe we have. That's peak oil, not necessarily peak fossil, and he was speaking in a unique context in the context of the COVID-19 pandemic. But is peak oil the only thing we need to worry about, right? So this is really great news. Look, here's renewable generation by source over the last 2 decades, essentially. I pulled these from the BP Statistical Review of World Energy 2019 edition. The 2020 edition, which has stats through 2019, will come out this June, so we're just a few weeks away from getting one more year on this plot. It's not going to change a whole lot, right? We see this growing exponentially. So this looks great, right? Renewables are growing. The prices for renewables are dropping, right, precipitously. So, right, Los Angeles was bidding out solar at 2 cents a kilowatt hour, including storage. The aggregate price was going to be about 3 cents per kilowatt hour for this project that they were bidding out. I think that's incredible, and that's something that I wouldn't have imagined even 10 years ago. Carbon Tracker has this great, forecaster that's been put in and said, well, here, if you want to know when we're going to have peak fossil fossil energy demand, right? You just need to say, what's the global energy demand growth, and then how fast are renewables growing? And you look ahead and you're like, well, it's 2029. It could be as early as 2022, or maybe it's going to be out at 2030. So their formula is right. That's pretty simple. How fast is global energy growing and how fast are renewables growing? But if you look at solar growth over the last 7 years or so, most of the last few years, there's even some sustained periods of negative growth. Right, we've rarely hit the 25% numbers that they're talking about in recent times when solar's been at scale, and so. Thinking about sustained 25% growth rates is pretty phenomenal. Maybe we'll get there. The other thing, my slides are slightly out of order. The other thing is that if you look at the annual change in energy demand and carbon emissions, it's closer to 3% than the 1 and 1.5% in their chart. In fact, global power demand grew by 3.7% in 2018. This was, of course, all pre-COVID, and so. Even accounting for the decreasing carbon intensity of our energy mix, our fossil fuel emissions, in fact, worldwide are growing every year rather than slowing. And so, right now that we're talking about bending the curve, the growth rate is increasing. It's not just that we're emitting more carbon, right? That the rate we're emitting it is increasing. So, if you put in actual numbers in here and look at 15% growth rates, now we're talking about dates that are 2 decades away before we see peak fossil. And so I think everything we do here to bend this curve really matters, and we need to think big. So the final point I want to make is, I think this is probably familiar to everyone. If you look at solar photovoltaic module production worldwide, I just pulled this off statista.com, right? The US, which used to dominate this market, is down here. I believe we're the 1% bar over here. So that's pretty depressing, seeing China owning 3/4 of the market for the fastest growing dominant renewable energy technology, and what's becoming the fastest growing of any electrical production technology. So we need to go faster. We'd like to manufacture locally. We'd like to manufacture with lower capital expenditure so that it doesn't cost $500 million to build a new plant, and we'd like to reduce the overall cost of energy. And so I'm going to try and convince you today that doing that with perovskites is a path forward. And so now I'm really going to get to the meat of my talk. So what's a perovskite? So you've probably, if you're in the solar field, you've probably heard about perovskites. Perovskite is just a crystal structure. It's the structure of calcium titanate. That's pictured down here. It's this cubic crystal lattice, and you can see this, it grows nice cubic crystals. But any material that has this ABX crystal structure, where you have right a cubic lattice with this corner sharing octahedra in here, is a perovskite. It's named after the Russian mineralogist Perovsky, and we're all standing above massive amounts of perovskites, because of course any mineral this structure, perovskite minerals are actually some of the most abundant minerals in the Earth's crust, and so we're all standing over billions and billions of tons of perovskite. Of course, that's not the perovskite that you make solar cells of. Certain special perovskites are direct gap semiconductors that absorb and emit light, such as methylammonium lead triiodide. And methylammonium lead triiodide would have a lead here. A methylammonium, and then leads, and then iodides in the A. So methylammoniums would be the A sites, lead would be the B sites, and the iodides would be the X sites here. right? So those would be methyl ammonium, the CH3, NH3, lead would be the B site, and iodides would be the X sites here to make a semiconductor. And so what is a direct gap semiconductor? That's a semiconductor that's better at absorbing and emitting light than silicon. So silicon's actually an indirect gap semiconductor. Interestingly, you can use quantum effects and composition to tune the band gap. So here's a series of solutions of perovskite nanocrystals. You can make them any color you want. They make incredibly pure light. This is a paper that came out of Alex Jen's group in collaboration with, actually in collaboration with one of Sarah's PhD contemporaries, Mark Ziffer at the UW. It makes incredibly narrow, incredibly pure light, and so people are exploring them for laser applications, for light-emitting diodes, for high-definition displays, for virtual reality displays. And so these are really very interesting materials. Oops, I have a slide problem here. I'll just read. But how do you make a perovskite into a solar cell? Well, you take that perovskite active layer and you sandwich it between an electron selective contact, in this case titania, could be anything that's electron selective. People use many, many different positive and negative electrodes, and then a hole or positive charge selective contact. This is a PowerPoint version from our CEI website. Here's a snazzier version from physics.org website. Basically, you see it's the same structure, and it's this perovskite layer that's really the key, and all these materials can then be deposited in different manners. So you sandwich all that together. The question solar people want to know is, how efficient is it? So here's the NREL efficiency chart. And what you see over here is that, so we want to look at yellow perovskite solar cells. Well, they were only discovered in the last decade. And so you start off here and they rise incredibly rapidly, and you're up here to 25.2%, which is phenomenal, right? This growth rate is fantastic, and this record efficiency is amazing. The record efficiency for a crystalline silicon solar cell, which has been basically in existence for almost 5 decades at this point, is 26.1. So already after less than 10 years, perovskites have essentially caught up to silicon, although don't have quite the efficiency. Of course, it's not entirely a fair comparison because we're using everything we learned from the 5 decades of science on silicon PV to quickly apply the same strategies to optimize halide perovskite photovoltaics. There's another exciting point on here that I'd like to talk about, and I'll expand more on at the end of my talk. But if you combine a perovskite solar cell with a silicon solar cell, literally by painting it or spraying it on top to make what's called a 2-terminal tandem cell, the current record for that is 29% efficient. And so a perovskite modified silicon solar cell is more efficient than any silicon solar cell that's ever been made. And so this is really cool. And why is that exciting? Well, as you guys all know, efficiency matters. And right now, this is a plot of essentially total cost as a function of country broken down by type. And the module cost is only a fraction. It's a quarter to a third, depending on whether it's utility or residential. The rest of it are things like soft costs, balance of systems, inverters, and so on. And the more efficient your solar cell is, the less of this you have to do per watt generated. And so even if your module price doesn't go any lower and you're stuck paying for labor and paying for permitting and so on, then the more efficient your solar cell is, the lower the cost of the delivered electricity. So pushing efficiency up is a way that science can help push costs down, even if science can't control permitting, financing, grid connection, cabling, inverter, and so on costs. All right, so we want to scale PV quickly. Efficiency is great. Module costs aren't free, so this is still one of the biggest bars up here, the orange bar for module cost. So can we bring that down even further to drive down cost? And why do I focus on driving down costs? It's because pretty much every model of how fast PV adoption continues to accelerate has cost as a very sensitive factor. And so the lower the cost, the faster people are going to continue to adopt PV. Of course, storage eventually is becoming a major option, a major obstacle today. But even in those models where storage becomes limiting, PV cost is still important. CapEx cost. So in an uncertain economic environment, if you're an investor, even if you know that you can make cheap PV, do you want to bet $1 billion or a multi-billion dollar factory on a uncertain regulatory future? And so can we find new ways to manufacture PV that drives down the upfront capital expenditures to build a factory? Energy payback. If we want to grow the solar industry rapidly, we need the solar cells to make a lot more energy than they cost to produce very, very quickly. And so, people have argued that right now what's happening in times where we grow silicon PV quickly, it's possible to reach a state where you're actually spending more energy to build the solar cells in any given year than all the solar cells that have previously been made produce. Now, if you stopped and waited, of course, the solar cells are always going to generate more energy than they took to produce over their lifetime. But if you're thinking about a multi-decade buildup to build a lot of PV, then building coal-fired power plants to power your silicon solar factories is probably not what you want to be doing. Environmental impact. This is the most manufactured semiconductor on the planet. So how does the environmental impact of manufacturing compare to across one technology and the other? And can we reduce installation costs further? So this is an old school slide. If you've seen a talk of mine, in the last 20 years, any solar researcher has shown a slide like this. It says, hey, electricity and actually primary power demand is huge. To make a difference on the climate problem, we need huge amounts of renewables. This is the amount of solar that we'd have to manufacture to have a significant impact. And we don't produce anything on that scale as a civilization, except paint and newspapers. And so, 20 years ago, people used to say, well, you need to figure out a way to make solar paint or solar newspapers, and people would say you can't do that. And this is where I think perovskites are incredibly interesting. So this is a slide that I found on Twitter, and I actually have to thank Sarah again. Being a technological Luddite, I was wondering, is Twitter useful at all? And at a group meeting one time, Sarah said, yeah, I follow scientists who post interesting papers on Twitter. And I know that's not how most people use Twitter, but that's how science nerds use it. And so, you find things like this, like here's a slide at a talk that I didn't go to by Oxford PV. And of course, take it with a grain of salt. They're a perovskite solar cell company, but, this is their analysis of how much raw material needs to go into manufacturing 1 megawatt of PV if you go from traditional crystalline silicon, which of course you have to grow, the ingots, dice the ingots into wafers, and then manufacture the wafers into modules. And that dicing, that kerfing process of the wafers loses a lot of silicon, and thus dramatically increases the energy intensity of silicon PV. And so 7 tons of silicon are needed versus 35 kilograms, to generate a megawatt of PV. And this is actually what the ink looks like for a perovskite solar cell. Now this is when I'm wondering whether GoToMeeting is going to handle this, but I think it looks like it's going to. So you can make an ink out of a perovskite semiconductor. You can dissolve it in a solvent. And here's a video. I'm not going to watch the whole 8 minutes of this.
5 minutes.
Go here. Here you go.
Mixture of methyl ammonium iodide.
So what you see is, this is how we would do it in the lab, See a student pipetting that ink onto a slide, It's a glass slide coated with a transparent conductor, and they spin it, and then they let it dry, and then they bake it for 15 minutes. And after they've baked it for 15 minutes, you see it turn black and absorbs light. And then another student here, AJ, is going to show the finishing the manufacturing process like we would do it in the lab. Let me pause that. Here's a demo, another video, So you have an ink, that you can print. And here's another video from NREL. It's a bit snazzier. They have professional video production. Fun fact, this hand here is the hand of Dave Moore, who was an undergraduate student at the University of Washington and is now a fellow at the National Renewable Energy Lab. So if I can go here to 33 seconds into this video, about here, this is Joe Barry at NREL talking. Okay, here you go. So what they've got is, this is a particular geometry of solar cell. It has an interdigitated back contact cell. So the solar cell contacts are on here. Here's the voltmeter hooked up to those electrodes. They have this is indoors in a fume hood, so they have an artificial light shining on the substrate, and they're gonna measure the voltage here. And they've got a paintbrush, and they've actually literally dipped this paintbrush in a solution of that yellow perovskite solar cell ink that I just showed you. You can watch as they paint it and let it dry, right? You see that they immediately start to get a voltage out. So what was science fiction 20 years ago is literally science fact today. We have inks. We literally have solar paint. And so of course you wouldn't do it with a paintbrush. You would do it with a machine like a roll-to-roll printer. And if any of you are familiar with the Washington Clean Energy Test Beds, which is part of the Clean Energy Institute, it's just off campus. It's an open access user facility that any business can come and use, any researcher can come and use. We have a roll-to-roll printer, and they can print electrodes. This is actually a slower printing, roll-to-roll printing of a perovskite. So you have this plastic sheeting here. On one end, it's unrolling. It's actually coming out through the machine here. It's being printed on in a slot die coder. It's extruding the ink out on here, then it dries, then they put the next layers on. You can actually see some of the process here where one of the facility managers is pouring some ink on. Now this is real time here. I'm not speeding the video up. The machine is actually being sped up. And you can see they're actually just rolling solar cell material off just like you would print newspaper. And so this, of course, this is a small scale, but this is the vision, this is the idea of why perovskite PV could be so transformative for manufacturing. So I mentioned energy payback time. This is the number of years for different technologies: crystalline silicon, polycrystalline silicon, CAD-TEL, different kinds of imagined production methods for halide perovskite PV, and you can see, right, they're a matter of months, and so the scaling of these could be done incredibly rapidly. The other thing that I mentioned is capital expenditure. That's come down for silicon PV. It's starting to level off. It's down from the $1 per watt peak that it was hovering around for a long time, but right, if you want to make a gigawatt of capacity, you still have to invest 400 million up front, and that's not a small investment in any environment. And so if you're thinking of deploying tens or hundreds of gigawatts of annual production capacity, right, the amount of capital is enormous, right? It's exceeding, right, the largest Intel chip manufacturing plants in terms of scaling. And so that's an enormous risk. And so if we can drive that down by letting people print on plastic sheeting rather than make high vacuum, high-end semiconductor process fabs, then we could bring that down and potentially bend the curve more. I don't want to get into the historic learning curves, right? Really, we don't know where perovskites would be. The hope is that if you look at silicon versus cadmium telluride, which is on here, that cadmium telluride would actually have an even steeper learning curve that would lie below CAD-TEL and result in even lower module costs. I mentioned environmental impacts. I mean, of course, this depends entirely on how the manufacturing would be done. And these eco indicator scores are, of course, difficult to parse, but if you compare, say, crystalline silicon, CAD-TEL, and different perovskite technologies, right, you can see that there's the potential, at least, to have the environmental impact for perovskite manufacturing be even lower than it is for crystalline silicon. And part of that is just a lower energy intensity needed, right? The energy needed to manufacture the perovskite is much, much lower. Now, here's another perovskite technology here. and you would probably never manufacture that way. And the reason this is so high, almost this entire orange bar here is the human health impact of using a gold electrode, because gold mining often uses toxic cyanide compounds, and that's the human health impact basically as soon as you switch. And so that's not related intrinsically to the perovskite, but it reminds us that as we design this new technology and try to scale it up, that there are things that we want to avoid, like using gold as an electrode in a large material. So this ability to paint perovskite solar cells like an ink is incredibly exciting. It allows you to make things cheaply that previously used to be impossible or so expensive that they were reserved for outer space and military applications. And that's a tandem solar cell. Many of you are probably familiar, but a tandem solar cell essentially allows you to harvest more of the sun's light than a single junction solar cell would be, and as a result, the total efficiency that you can obtain is higher. And so a perovskite solar cell tandem would look something like this. You'd have a top cell that would harvest the blue light, and then the red light would pass through, and the red light would be harvested by the silicon cell, and then the high energy of the blue photons would be converted to voltage, whereas it would just be converted to heat if the silicon solar cell was allowed to absorb all of that blue light. And so you, of course, can make them separately and stack them in a 4-terminal configuration, but that tends to be very complicated to design the circuitry and is generally disfavored. And with an ink, you can simply put a junction layer in between. This is an unsolved technological problem that's not unsolved. This is an active area of research as to what the best layer of this charge recombination layer should be. You paint on the perovskite solar cell, finish with the top electrode. This is just another ink, right? It's like going from black and white to a color newspaper, right? It is a little bit more expensive, but not tremendously relative to the overall cost. And now you have a 2-terminal tandem cell, and those 2-terminal tandem cells, that's the 29.15% efficiency point that I showed you at the start of the talk on the NREL efficiency chart. That was just this January, right? The Helmholtz Center in Berlin got a 29.15% efficient tandem cell, and here they have it encapsulated in a giant block of glass to make sure that it lives for a long time. And now I'm going to speculate a little bit. Why else might printed flexible solar cells be interesting? If you look at the non-hardware balance of systems costs in mature markets like Germany, right? It's continued to come down a little bit, and I acknowledge this is older data, but installation and labor remains a significant fraction of the cost of particularly residential PV. And so it's fun to speculate, well, if you didn't have large, heavy, bulky, fragile, glass encapsulated silicon modules, could you have installation costs that were dramatically lower if you had flexible PV that you could unroll and staple down with a staple gun? Right, it's not ever going to be that simple, but the less expensive the material, often the more tolerance that you'll take in installing it, and the cheaper the installation costs can be driven down. So this is interesting, and this is, I'll acknowledge entirely, it's purely speculative, but I think moving to new technologies that are manufactured in entirely different ways, that have entirely different cost structures and physical form factors, has the potential to drive PV down, PV costs down, and installation costs down in ways that we haven't even explored yet. So are we there yet? Certainly not, although I'm there if we want to have time for questions. Dozens of companies worldwide are commercializing perovskite PV. There's I think at least a half a dozen in the US. There's many more. There's a half dozen that have had a high public profile. Europe and Asia have launched major national and sort of continent-wide investment programs. The Department of Energy, particularly the Solar Energy Technology Office, is investing heavily in perovskite PV in the US, at least at the individual institution level. They haven't formed these large national consortium, like we have a battery consortium, right? The Battery 500 consortium. We don't have a comparable scale project in solar, at least not in perovskite solar. Actually UW was part of, along with National Renewable Energy Lab, a group of partners that have been trying to stand up a US-based consortium based on regional and state investments. Obviously there's challenges. There are roadblocks that need to be overcome. That's my timer to remind me to get to my last slide, and here I am. Right, this is a new technology. Perovskite solar cells have passed many of, if not most, of the lifetime tests for standard silicon PV. And so if you believe those tests, you could extrapolate that they have 10, 20 plus year lifetimes already. But what we would like to do is get to 25-year lifetimes. And a more important question is, it's a different material. So can you trust a test that was developed for silicon to give you an accurate lifetime prediction for perovskite, right? There are acceleration factors. If you heat it up by this much, how much do you actually accelerate the aging? When you put it under light that's more intense than the sun, how much do you actually accelerate the aging? Those are really poorly understood, and there's a lot of research going in to understand the mechanisms of degradation, and hopefully we'll have answers to those in the future. If you're really interested, Mike McGee's group at UC Boulder and NREL published a review just at the end of last year, and that goes into 30 pages of technical detail about what those challenges are. Lead. So you probably perked up at the beginning when I said methyl ammonium lead triiodide. How much of an issue is the lead? I don't want to be one of these people that says it's not an issue. I think probably scientifically it may not be an issue, but just from a public acceptance standpoint, it is a real issue. And so you can't tell someone something like, oh, well, your solar cell has less lead in it because it's so thin than your TV does because your TV used to have lead solder in it, right? You can't tell people, oh, well, your car has a pound of lead in it. Your solar cell on your roof has less lead in it than your car battery, right? That doesn't make people feel safer. So I think what we're going to need to do is we're going to need to find ways to make sure the solar cells are completely encapsulated and none of the lead can ever get out, or develop lead-free perovskites. And those are both active areas of research. There was a really cool article that came out earlier this year. Lead binds to many materials very, very strongly, and by essentially putting a layer of special polymer intimately mixed with the solar cell, they showed that you essentially could grind up a perovskite solar cell, dip it in water, and almost no lead was dissolved in the water as a result. So there are very interesting technical solutions to that. Manufacturing, right? I showed you lab scale manufacturing or small pilot line manufacturing. So in principle, that's one of the exciting things about perovskite PV is that you could scale it up, but no one's done that yet. So that's really the question. Oxford PV and other companies are already building pilot lines. Oxford PV is building their pilot line in Germany. We would have loved if they built it in Washington. They did have some brief discussions with WCET, but I think for a variety of reasons they wanted to be based in Europe, given that they were founded in Oxford. And metrology. What tools can support these activities, right? If you're manufacturing something at scale, you have to be measuring it in a well-characterized fashion. And so since it's an emerging technology, there's a lot of hand-in-hand science and engineering development that's still going on. And so I mentioned US map. If you go to www.usa-perovskites.org, it's probably a pretty bare bones website, but it's a consortium that's been formed from NREL, University of Toledo, the Research Triangle in North Carolina, University of Washington, and the half dozen sort of known major US perovskite PV companies that have been announced and exited stealth mode at this point in time. And we're hoping that we can make this a real technology that you can buy in the near future. So that's my 45 minutes, and I think we've got 15 more minutes if people have questions. I'd love to see what's what's going on. I think I have to exit my slides before I can see you guys again.
David, I can read the questions too for you if you want to leave.
Oh, great.
Stuff up.
I'm trying to get back to GoToMeeting, but the way I was able to figure it out before, yeah, that would be great. Just read me some questions.
Yeah, I'll just read some questions. So, and just a reminder, if you want to ask David some questions, you can put them in the chat box and I will read them. So the first one we have is about kind of form factors. So the question is, can this paint be used on the exterior of an EV to recharge batteries on the road? Maybe it needs an enamel base to prevent road weathering?
So that will be, the short answer is yes, absolutely, because you can make a flexible form factor solar cell, right? So you could make solar modules, conform them to the auto body. Some of the I think first research that this is being done in UAV applications, right, to extend the endurance of electrically powered UAVs, where you want to have conformal PV along the wing surface, right? You don't want to have a flat PV spoiling the airflow. And so absolutely, you can make conformal PV out of it. The corrosion issue would be handled almost entirely by the same encapsulation technologies that are going to be needed to make it resistant to weathering, aging, water ingress. Right, just being out in the field, I think the standard test requires it to survive like baseball-size hail. Obviously, being on an auto body would probably require even further, further reinforcement. Your car window gets chipped all the time by, right? How many of you had to replace your car window because a rock fell off a truck? And so now if a rock fell off a truck and chipped the solar cell, any solar cell technology, silicon, right, is going to have water ingress and have a problem. So it's in principle possible. The encapsulation would be an issue. And then the final thing actually is that it does make sense for some slow charging of your electric vehicle, but generally the power output of your electrical vehicle is an order of magnitude larger than the power input of your solar cell. So in terms of recharging your solar cell on the go, you don't get a huge amount of bang for your buck. Although you could conceivably extend the range and you could conceivably have your car charge while it's out in a parking lot. Personally, I think that having smart charging everywhere where the cars can give up and receive power wherever they're plugged in will be more of an impact. But that's, again, it's an area I don't know, and people are trying to do all of those. It's a great question.
Great. And so maybe a kind of related question is, what's the recyclability of perovskite panels, quote unquote? Can perovskite be extracted from exhausted or retired panels for reuse?
So the answer is yes, it could be. It should be much easier to do than with many other materials because it's soluble, right? So you could wash it off and dissolve it pretty easily. Now, if you started putting on gettering layers that made it impossible for the lead to get out, you might obviate the recyclability. The question of would you ever actually want to recycle it becomes another question. There's actually a very small amount of active layer. It's typically a micron thick or less. So a human hair is maybe 100 microns thick. So the active layer of the solar cell is 1/100th the thickness of a human hair. And so in fact, there's incredibly small amounts of material per unit area relative to the package. And so since it's so cheap to begin with, it may be a question of finding permanent disposal options rather than actually recycling it over the long term. That's an active area of research. People are publishing papers right now saying, like, how are we going to manage end of life issues for perovskite PV? And as you probably know, that's an issue for all of solar technology right now. So the CadTel manufacturers guarantee that they will take back your cadmium telluride, right? Of course, cadmium also being not particularly environmentally friendly. And there's not really a regulatory framework. Right now, companies guarantee we'll take back your solar cell in 30 years. But if the company is not here in 30 years, then the guaranteed recycling program that's supposed to be there in 30 years won't happen. So, so that's a long answer to a short question, but in principle, yes, technologically, there's no technological barrier to recycling the perovskite. In fact, chemically, it should be much easier than for many other PV technologies. Economically, whether it would be economically feasible because the material is so cheap is a second question. And so managing end of use and end of life issues is something we do need to think about. And broadly for PV, I think if any of you have policy influence, Sarah, is there any chance that we could have like a national trust, right, where you pay in a certain percentage of your price when you buy the module and that goes into a trust fund? And if a PV manufacturer has gone out of business, then that trust fund goes to help provide the end of life cycle recycling that was needed when you bought it up front. So
it's actually a great question. And yeah, sorry, David, go ahead.
Yeah, I don't know whether we're going to get there or not.
And Washington has actually got a first in nation policy on looking at solar manufacturing. So where manufacturers would need a plan for end of life. So anyway, if you're interested in that, Department of Ecology in our state is looking into that. So yeah,
Awesome.
David, another question about synthesizing these these materials. So the question is, what are some synthesizing methods that perovskites have used for solar cells? And it's mentioned that there's a combustion method to synthesize an oxide perovskite. Can you use this same method for perovskite solar cells?
I'm not familiar with anyone using a combustion synthesis to make a halide perovskite. And the reason for that is the oxide perovskites typically need very high temperatures to calcine. The halide perovskites typically are stable at, and this is actually one of the issues with lifetime and stability, will typically decompose at maybe 150, 200 C. Sarah probably knows the numbers better than me because she studied phase transitions in the perovskites for part of her PhD.
Not anymore, but.
But the synthesis methods, the two primary methods that are used right now, one is a physical vapor deposition, which is done by co-evaporation. And so people will essentially sublime the perovskite precursors in the stoichiometric ratios, the right elemental ratios of methyl ammonium iodide and lead iodide co-evaporated together. So they'll heat up lead iodide, methyl ammonium iodide in the right ratio. And those two vapors will combine and then condense on a substrate in a vacuum chamber. And then the other method is essentially a solution synthesis, and you dissolve your methyl ammonium iodide and your lead iodide into a solution, right? And you make an ink, and then you let that ink dry. And there's it's more complicated than that because there's lots of subtleties with small amounts of additives and surfactants, right, that change the surface properties, that change how fast the ink dries, how well it wets the surface. And so, right, there's a lot of science that goes into it, but it essentially is that simple. You dissolve the two precursor compounds together, you get a yellow solution, you let it dry, and then you heat it up to roughly 100 or so degrees. If you watch that YouTube video that we had earlier, we show a particular recipe and there's a heat ramp, right? That you heat up at a certain rate and then cool it down at a certain rate to give you a good crystal structure for the perovskite. I don't know that combustion synthesis would be impossible, but combustion may get you too high of a temperature that may actually decompose some of the perovskite. It may volatilize some of the organic components out of the perovskite that wouldn't happen with a pure oxide perovskite.
And then David, another, oh, I'm sorry, go ahead.
Yeah, no, go, please go.
Yeah, we've got some great questions coming in. I want to make sure we get to them. Another material question. What color is ideal? And can different colored perovskite paint be a consumer option?
So absolutely. So the ideal color has to do with what's the ideal color to absorb the sun. And that tends to be around 1.5 electron volts band gap. So the ideal color is black because it absorbs all of the sunlight. It's actually infrared, but since we can't see infrared light, our eye perceives it as black. You can make perovskites in any color, as you saw. And that's what facilitates their incorporation into a tandem cell. So you would have a perovskite that's actually a very, very dark red, and that absorbs all of the red, all of the blue light, and then the infrared light is absorbed by the silicon cell. That's what happens in the, in these tandem cells over here, right? The blue, right, and up to the red light, and this is just a cartoon, but then the infrared light passes through to the silicon cell. And yes, if you wanted designer color options, you could do that. You actually can do that with silicon PV. You can put reflective layers on the surface to make them appear different colors. Of course, whenever you throw away a little bit of light to get a color for a visual appearance, you decrease the efficiency. But for some architectural applications, that's highly desirable. So it's possible, yeah.
Yeah, and there's kind of another related question about how these thin films then might help improve residential scale installations, aesthetically speaking. So through lamination assemblies with glass or wall cladding.
Yeah.
Actually, no, don't know the word cladding, so hopefully I'm saying that right.
Yeah, claddings, building integrated PV are areas that are really being explored for perovskite as well. So because of the unique form factors and the ability to deposit on different kinds of substrates, there are a number of startup companies that are exploring niche applications for building integrated PV, before they hope to scale to really large scale applications like, say, solar shingles or giant glass paneling for large commercial installations, like giant glass office towers. There are perovskite technologies that give you really good color rendition. So one issue there is the ideal actually is that you want the glass to be a neutral gray, right? To not make your light look pink or blue or purple. And there's a way to do that with perovskites that actually lets regular sunlight through, but then converts the rest of it to electricity, so that you get the, say, 20% transmission window that you wanted, and it doesn't make your office look pink to give everyone sort of a headache at the end of the day. So yeah, that's a great question too.
Yeah, and then kind of keeping on this material aspects trend, can perovskites be combined with materials that change brightness or darkness with temperature to be able to implement thermal and PV from solar in the same material?
Not that I know of. I've not seen any of that. That would probably require a lamination of some kind of solar cell and then some kind of material that's thermally responsive or externally controlled to regulate the transmission. So you're saying you want a window that basically it reflects light during part of the day and lets light and heat through during the other part of the day. I don't know of a way to do that with perovskites at the moment. So certainly the solar cell side is great, but the change in transmissivity with temperature and bias, I don't know a way to do with the perovskites.
Great. Well, it looks like we have time for maybe one more question. So we have this one about what publicly traded companies, if any, are making the most headway on commercializing perovskite, and maybe speak a little bit about the U.S. map work.
Oh, yeah, that almost sounds like one I should steer away from, right? I'm not supposed to endorse I'm not supposed to endorse particular companies or say one is making more headway than another. If you go to the US map website, it lists the 6 companies that have been these are all US based. So US map was particularly restricted to be right with the US manufacturing focus. And so those are the 6 US companies that are probably the best known. And if you go to the US map website, you can read the list of them there. There are other international companies that a simple Google search will turn up. I already mentioned Oxford PV. They're probably the best known. They came out of the University of Oxford, obviously. I don't believe they're publicly traded at the moment. So yeah, I'll leave it at that.
All right, we won't get you into too much trouble then. And actually, we have time for the last question that I see here in the chat, which is for thin film solar cells, is CZTS a promising research area?
So that's a complicated question. Actually, Sarah worked on some of that during her PhD as well. There are a number of groups still actively working on CZTS. For the most part, CZTS has seen substantial disinvestment. One reason for that has been the fact that perovskites have been able to yield higher efficiency more quickly. The other reason is that a lot of theorists have basically concluded that the complex ternary structure of CZTS has thermodynamic defect levels that are intrinsically unstable that will pin the voltage. So I guess what that means is that when you try and grow CZTS, what the material wants to do is have defects in it, and those defects will always make it really hard to obtain the theoretical limit of voltage from that cell. And so people have said, well, here you have a material that really wants to not be an efficient solar cell, although it has all these other attractive prospects. And I'm sure if there was a CZTS aficionado here, they would tell me why they have hope for CZTS still. But I would say there's sort of a consensus view that CZTS will be challenging because of the intrinsic number of the ease at which defects form in that material. So hopefully I don't upset CZTS people by saying that. I mean, we continue to collaborate with people who study CZTS, so it's by no means a dead technology. It's just there are some real intrinsic challenges with it.
Great. Well, David, thank you so much. We're at time. I just want to say on behalf of Solar Washington that we really appreciate having you on today to walk us through what is possible in this world. And really, I think the idea of bringing some solar manufacturing back to the U.S. is just wonderful. So excited to see where the U.S. map work goes.
Yeah, me too. Well, thanks for having me, and thanks for all the great questions. That was really fun. So
yeah. All right, everyone. Thank you so much. And
thank you, David. Thank you, Sarah. And thanks, everyone, for being on this call. Thanks for attending. Stay safe and have a great rest of your day.
You too.
Thank you.